On the evening of September 18, 1980, at Launch Complex 374-7, near the small town of Damascus, Arkansas, a routine maintenance operation inside a Titan II intercontinental ballistic missile silo began a chain of events that would unfold over 9 tense hours and end with one of the most dramatic nuclear weapons accidents in American history. The Titan II system represented one of the most powerful components of the United States strategic nuclear arsenal during the Cold War. Unlike earlier missile systems that required lengthy fueling procedures before launch, the Titan II used a storable liquid propellant combination that allowed it to remain fully fueled and ready for immediate launch inside hardened, underground silos. Each missile carried a W-53 thermonuclear warhead with an estimated yield of approximately 9 megatons, making it one of the most powerful nuclear weapons ever deployed in the U.S. arsenal. The missile itself stood more than 100 feet tall inside a reinforced, concrete silo designed to withstand shock waves from nearby nuclear explosions. Launch crews stationed at underground control centers monitored the missile around the clock, maintaining readiness in case orders were ever issued to fire it toward its designated target in the Soviet Union. Although the system had been in service since the early 1960s, by 1980, the Titan II program was widely regarded within the Air Force as aging and increasingly difficult to maintain. The missiles relied on highly volatile propellants known as Aerozine 50 and nitrogen tetroxide, chemicals that could ignite spontaneously upon contact and produced extremely toxic vapors. Maintaining the missiles required regular inspections and repairs carried out by specialized maintenance teams who worked in confined spaces around the missile structure deep inside the silo. On that September evening, a maintenance crew from the 308th Strategic Missile Wing had been assigned to conduct routine work on the Titan II missile at Launch Complex 374-7. The task involved checking pressure levels in the missile's fuel system, a procedure that required technicians to access components located several stories down inside the silo structure. Because the Titan II remained fully fueled at all times, technicians performing maintenance had to operate carefully around pressurized tanks containing thousands of gallons of volatile propellants. The maintenance crew included 2 airmen trained in the specialized procedures required for working near the missile. Wearing protective gear and carrying tools designed specifically for use in the confined environment of the silo, the technicians descended the elevator that led down into the missile complex. The Titan II silo was an enormous underground chamber, reinforced with thick concrete walls and surrounded by a network of service platforms that allowed technicians to access different sections of the missile. As the crew began their assigned task, one of the technicians attempted to remove a pressure cap located on the missile's fuel system using a ratchet wrench attached to a long extension socket. The tool was necessary because the pressure cap was located several feet away from the technician's position, requiring the extension to reach the fitting. During the operation, something unexpected happened. As the technician worked with the wrench, the heavy socket attached to the extension slipped from the tool and fell. The socket, weighing several pounds, dropped through an open service platform and fell approximately 70 feet before striking the side of the missile's first-stage fuel tank. The impact punctured the thin metal skin of the tank, creating a hole through which Aerozine 50 fuel began to leak rapidly into the silo environment. The moment the socket struck the missile, the technicians immediately realized the seriousness of the situation. The Titan II's propellant tanks were not designed to withstand impacts from falling. Objects, and even a relatively small puncture, could release large amounts of fuel. The maintenance crew quickly reported the accident to command personnel monitoring operations from the Launch Control Center. Within minutes, alarms began indicating that fuel was leaking inside the silo. Aerozine 50 is a highly volatile mixture of hydrazine and unsymmetrical dimethylhydrazine used as a rocket fuel. When exposed to the oxidizer nitrogen tetroxide, it ignites spontaneously without the need for an external ignition source. In the Titan II missile, the two propellants were stored in separate tanks until the moment of launch, when they would mix in the engine combustion chamber to produce enormous thrust. However, if the two chemicals were accidentally released and came into contact outside the engine system, they could ignite or explode. As fuel began pouring from the punctured tank, technicians evacuated the immediate work area and sealed the silo entrance while emergency procedures were initiated. The escaping fuel vaporized rapidly in the warm environment of the silo, producing toxic fumes that filled the chamber. The leak created not only a fire hazard, but also a serious chemical hazard for anyone entering the silo without specialized protective equipment. At the Launch Control Center, officers responsible for the missile complex began assessing the situation. The Titan II remained armed with its 9-megaton warhead, and the presence of volatile fuel vapors inside the silo raised concerns about the possibility of an explosion. Yet the missile itself was not designed to detonate its nuclear warhead under these conditions. The W-53 warhead incorporated multiple safety systems intended to prevent nuclear detonation unless specific launch and arming procedures were completed. Nevertheless, an explosion of the missile's propellant tanks could potentially damage the warhead or propel it out of the silo. The officers overseeing the situation therefore faced a complex problem. They needed to determine whether the leak could be stabilized or whether further action was required to prevent the situation from escalating. As the hours passed, the leaking fuel continued to accumulate inside the silo. Emergency teams equipped with protective suits attempted to evaluate the damage and determine how much fuel had escaped from the tank. Because the missile remained fully fueled, the puncture allowed thousands of gallons of propellant to drain gradually into the silo structure. The Titan II missile had been designed with certain safety procedures for handling fuel leaks, but those procedures assumed small leaks that could be contained quickly. In this case, the hole in the tank allowed fuel to escape continuously, creating a growing pool of volatile liquid at the bottom of the silo while toxic vapors filled the chamber. Meanwhile, command authorities debated whether nearby communities should be evacuated as a precaution. The missile complex was located in rural Arkansas, but farms and homes existed within a few miles of the site. Despite the potential risk, the Air Force initially decided not to order a large-scale evacuation, believing that the situation could be controlled. Throughout the night, the leaking missile remained unstable, while technicians and officers struggled to decide on the safest course of action. Specialized teams trained in hazardous materials response were dispatched to the site to assess whether the leak could be sealed or whether the missile's fuel system could be vented to reduce pressure. These teams faced extraordinary risks because entering the silo meant exposure to toxic vapors and the possibility of ignition if the fuel and oxidizer came into contact. As midnight approached, the atmosphere inside the silo had become saturated with volatile chemicals. The Titan II missile still stood inside the chamber with a punctured fuel tank, while thousands of gallons of propellant continued leaking into the structure. The 9-megaton nuclear warhead remained mounted at the top of the missile, its safety systems intact but surrounded by an increasingly dangerous environment. The hours that followed would determine whether the accident remained a dangerous but contained incident or escalated into a catastrophic explosion capable of destroying the entire missile complex. As the night progressed at Launch Complex 374-7, the situation inside the Titan II missile silo became increasingly unstable, while military officials struggled to determine how to respond to a problem for which no clear precedent existed. The puncture in the missile's first-stage fuel tank continued releasing Aerozine-50 into the silo environment, and the volatile fuel began accumulating in large quantities at the bottom of the launch complex. The Titan II silo was not a simple vertical shaft, but a vast underground structure extending many stories below ground level, containing service platforms, equipment rooms, and access corridors surrounding the missile itself. As the fuel leaked downward through these spaces, it began forming pools in lower sections of the complex, while vapors rose upward through the chamber. The fuel's chemical properties made the situation particularly dangerous. Aerozine-50 produces highly toxic fumes that can quickly incapacitate personnel without protective equipment, and its ability to ignite spontaneously upon contact with nitrogen tetroxide meant that any accidental mixing of the two propellants could trigger a violent reaction. The missile's oxidizer tank still contained thousands of gallons of nitrogen tetroxide above the punctured fuel tank, and if the structural integrity of the missile were compromised further, the two chemicals could mix. At the Launch Control Center, located some distance from the silo, officers responsible for the missile complex monitored the growing emergency. Communication between the control center and personnel on the surface of the silo provided updates about fuel levels, vapor concentrations, and the condition of the missile structure. Technicians who had initially been working inside the silo remained outside while emergency procedures were discussed. Strategic Air Command maintained extensive protocols for handling accidents involving nuclear weapons, but the scenario unfolding at Damascus involved a unique combination of hazards: a fueled intercontinental ballistic missile, a leaking propellant tank, toxic vapors filling the silo, and a 9-megaton nuclear warhead mounted on top of the missile. Commanders had to decide whether to attempt repairs, vent the silo, or simply wait for the propellant to dissipate naturally. Each option carried its own risks. Entering the silo could expose technicians to toxic fumes and the possibility of ignition. Venting the silo might release dangerous vapors into the surrounding environment. Waiting too long could allow the situation to deteriorate further if structural damage to the missile worsened. During the early hours after the accident, the Air Force began deploying specialized teams trained to operate in hazardous environments involving missile propellants. These teams wore protective suits designed to shield them from toxic chemicals and carried breathing apparatus that allowed them to enter areas where vapors had accumulated. One of the primary objectives was to determine the size of the puncture in the fuel tank and whether the leak could be slowed or contained. However, the complexity of the Titan II silo made it difficult to obtain accurate information. The missile was surrounded by service platforms and structural supports that obstructed direct visual inspection of the damaged tank. Instruments measuring vapor concentration indicated that the atmosphere inside the silo was becoming increasingly saturated with fuel vapors. This meant that even a small spark or mechanical failure could potentially ignite the mixture. Despite the growing danger, the decision was made to send a team back into the silo to gather additional information about the leak. 2 technicians equipped with protective gear descended into the upper levels of the complex while monitoring equipment measured the concentration of toxic gases around them. Their mission was to determine whether the missile's propellant valves could be manipulated to reduce the pressure inside the tank and slow the leak. However, as the technicians approached the levels closest to the missile itself, they encountered conditions far more hazardous than expected. The concentration of vapors was extremely high, and the smell of the propellant was overwhelming even through their protective equipment. Instruments indicated that the environment was approaching levels where ignition could occur if the oxidizer system were compromised. Throughout these hours, questions continued to arise about whether nearby communities should be evacuated. The missile complex was located in rural Arkansas, but several small towns and farms existed within a few miles of the silo. A catastrophic explosion inside the complex could produce a massive blast wave and scatter debris across the surrounding countryside. Yet the Air Force initially resisted ordering a full evacuation, partly because officials believed the missile's nuclear warhead would not detonate even if the propellant exploded. Nuclear weapons are designed with safety mechanisms that prevent the nuclear reaction unless specific conditions are met, and the W-53 warhead atop the Titan II required a carefully controlled sequence of electrical signals and environmental triggers to arm itself. Nevertheless, an explosion of the missile's fuel tanks could still produce a powerful conventional blast capable of destroying the silo and throwing debris across a large area. As the night continued, the fuel leak worsened. The punctured tank allowed Aerosine 50 to escape continuously, and the missile's internal pressure systems ensured that the propellant flowed steadily through the hole created by the fallen socket. Engineers monitoring the situation realized that as more fuel escaped, the structural stability of the missile might be compromised. The Titan II missile relied on internal pressure to maintain the shape and strength of its propellant tanks. If enough fuel leaked out, the tanks could collapse or shift, potentially causing the missile to fall within the silo. Such a collapse could rupture the oxidizer tank or trigger a violent reaction between the two propellants. Shortly after midnight, additional emergency teams arrived at the site to assist with the crisis. These personnel included specialists familiar with the Titan II system who had been flown in from other missile bases. Their presence reflected growing concern within Strategic Air Command that the accident might escalate beyond the control of the local crew. By this point, several hours had passed since the initial puncture of the fuel tank, and the silo environment had become saturated with fuel vapors. Command authorities continued debating possible responses while monitoring conditions inside the complex. The technicians who had entered the silo earlier eventually withdrew after concluding that they could not safely access the damaged tank. Meanwhile, the missile itself remained standing inside the silo, its warhead armed but not activated, while volatile chemicals continued leaking from the punctured tank. Sensors detected increasing concentrations of vapors near the upper levels of the complex, suggesting that the fuel was spreading throughout the structure. As the hours passed, the possibility that an ignition might occur became increasingly difficult to ignore. The Titan II missile system had long been known among technicians as a powerful but hazardous technology because of the volatile propellants it used. Maintenance crews working on the system were accustomed to strict procedures designed to prevent accidents involving those chemicals. Yet the accident triggered by the dropped wrench had created a situation that few had imagined possible. A fueled intercontinental ballistic missile leaking propellant inside its own silo while carrying one of the most powerful nuclear warheads in the American arsenal. By the early morning hours of September 19th, the crisis had entered its most dangerous phase. Nearly 9 hours had passed since the socket punctured the missile's fuel tank, and the silo had become a volatile chamber filled with flammable vapor and thousands of gallons of leaked propellant. The missile structure remained intact for the moment, but engineers monitoring the situation feared that further deterioration could occur at any time. Emergency teams on the surface prepared contingency plans, while command authorities continued evaluating whether additional personnel should enter the silo to attempt further inspection. The decisions made during these final hours would determine whether the accident ended with the safe stabilization of the missile or with a catastrophic explosion inside the underground complex. As the early morning hours of September 19th approached, the atmosphere inside Launch Complex 374-7 had become dangerously unstable, and commanders overseeing the situation realized that the leaking Titan II missile had created a scenario that no maintenance manual had fully anticipated. Nearly 9 hours had passed since the socket fell from the technician's wrench and punctured the missile's first-stage fuel tank, and during that time, thousands of gallons of Aerozine 50 had escaped into the silo environment. The toxic fuel had pooled in lower levels of the complex, while vapors filled the massive chamber surrounding the missile. Sensors indicated that the concentration of propellant fumes had reached levels that made further entry into the silo extremely hazardous, even for personnel wearing protective suits. Yet the condition of the missile itself remained uncertain. Engineers monitoring the system worried that the continuing loss of fuel pressure inside the tank could cause structural failure within the missile body. Titan II propellant tanks were designed to maintain their shape under internal pressure. As fuel escaped through the puncture, the pressure inside the tank gradually dropped. If the pressure fell too far, the missile could lose structural stability, potentially causing it to collapse or shift inside the silo. Shortly after 3 a.m., commanders at the scene made the decision to send another team into the complex to gather more information about the condition of the missile and the concentration of fuel vapors near the upper levels of the silo. 2 technicians wearing protective equipment entered the access structure and descended toward the service platforms above the missile. Their task was not to repair the puncture, but to collect readings that might help determine whether the situation was becoming more dangerous. The technicians carried instruments designed to measure vapor levels and detect changes in pressure within the missile's tanks. As they moved downward through the silo structure, the smell of propellant became increasingly intense. Even through their protective gear, the fumes were difficult to tolerate, and their instruments indicated that vapor concentrations were extremely high. While the technicians were inside the complex, conditions around the missile continued to deteriorate. The steady leak of fuel had weakened the structural balance of the Titan II's first stage. The missile's design relied on precise alignment within the silo, and the loss of pressure in the fuel tank increased the risk that the vehicle could buckle or tilt. At approximately 3 a.m., without warning, the internal structure of the missile failed. The first stage tank collapsed suddenly, releasing a massive cloud of fuel vapor into the silo. Almost instantly, the mixture of propellant and oxidizer gases ignited. The resulting explosion was enormous. The blast ripped through the underground complex, destroying the silo structure and sending a fireball shooting upward through the opening at the surface. The force of the explosion was powerful enough to launch the Titan II missile itself out of the silo. The missile's massive body was torn apart by the blast as it was propelled upward through the silo opening. Pieces of the rocket structure scattered across the surrounding farmland, while the explosion shattered equipment and concrete walls inside the launch complex. The 9-megaton W-53 nuclear warhead mounted atop the missile was thrown hundreds of feet into the air before landing in a ditch several hundred feet away from the destroyed silo. Remarkably, The warhead did not detonate. Nuclear warheads are designed with multiple safety systems that prevent a nuclear explosion unless a very specific sequence of arming signals occurs. The conditions created by the missile explosion did not provide those signals, and the warhead's safety mechanisms functioned as intended. Although the conventional blast destroyed the silo and scattered debris across a wide area, the nuclear device itself remained intact. The explosion killed one of the technicians who had entered the complex shortly before the blast and injured several others involved in the emergency response. Emergency crews rushed to the scene as flames and debris continued burning around the destroyed launch site. The warhead, which had landed intact in a roadside ditch, was quickly located by Air Force personnel. Specialized nuclear weapons teams were dispatched to secure the device and ensure that it remained stable. Within hours, the warhead was transported away from the site under heavy security while investigators began examining the remains of the silo to determine exactly what had happened during the final moments before the explosion. For residents of the rural communities surrounding Damascus, the blast was unlike anything they had experienced before. The explosion shook houses miles away from the silo, and the sound of the blast could be heard across much of the surrounding countryside. Many residents initially believed that an earthquake or industrial accident had occurred. Only later did they learn that the source of the explosion had been the Titan II missile complex located near their town. Although the nuclear warhead had not detonated, the destruction of the silo created a dramatic scene of twisted metal, shattered concrete, and debris scattered across fields. In the days that followed, investigators from the Air Force and the Department of Defense began reconstructing the events that led to the explosion. Their analysis confirmed that the accident began with the dropped socket that punctured the missile's fuel tank. The leak allowed thousands of gallons of Aerozine 50 to escape into the silo, creating a volatile environment where fuel vapors accumulated over several hours. As the fuel continued to drain, the pressure inside the tank fell until the structure collapsed. The collapse released additional fuel and vapor into the silo, where it ignited almost immediately in the presence of the oxidizer gas. The resulting explosion destroyed the missile and the launch complex, but did not trigger the nuclear warhead's detonation sequence. The destruction of Launch Complex 374-7 represented the most dramatic accident involving the Titan II missile system during its years of operation. The program had long been known among technicians and engineers as one of the more hazardous components of the nuclear arsenal because of the volatile liquid propellants used by the missile. Maintenance records dating back years had documented numerous leaks, equipment failures, and safety concerns associated with the system. Yet the missiles remained on alert across several bases in the United States because they provided an important component of the country's strategic deterrent force. The Damascus accident exposed the risks inherent in maintaining such powerful weapons in underground silos while relying on maintenance procedures that required technicians to work in close proximity to fully fueled missiles. Although the explosion destroyed the missile and its silo, the fact that the nuclear warhead remained intact prevented what could have been one of the most catastrophic nuclear accidents in American history. The W-53 warhead's safety systems functioned as designed, ensuring that the nuclear reaction required for detonation could not occur under the chaotic conditions produced by the blast. Nevertheless, the accident raised serious questions about the safety of the Titan II system and the procedures used to maintain it. As investigators examined the wreckage and reviewed maintenance records, they discovered evidence that the missile program had experienced repeated technical problems over the years, issues that had been documented in classified reports long before the dropped wrench triggered the disaster at Damascus. The lessons drawn from those investigations would eventually contribute to the decision to retire the Titan II missile system entirely during the 1980s. In the aftermath of the Damascus explosion, the U.S. Air Force launched an extensive investigation to determine exactly how a routine maintenance procedure had escalated into the destruction of an intercontinental ballistic missile complex carrying one of the most powerful nuclear warheads in the American arsenal. Teams of engineers, safety investigators, and nuclear weapons specialists arrived at the site within hours of the explosion to examine the debris field and reconstruct the sequence of events that had unfolded during the 9 hours between the dropped socket and the final blast. The wreckage of the Titan II missile lay scattered across the surrounding farmland, while the silo itself had been almost completely destroyed by the explosion. Massive sections of reinforced concrete had been blown apart, and the underground launch complex was filled with twisted metal, fuel residue, and shattered equipment. Investigators carefully documented the position of debris fragments, examining pieces of the missile structure to determine how the internal tanks had collapsed and how the propellant mixture had ignited. Their findings confirmed that the puncture created by the falling socket allowed Aerozine 50 fuel to escape continuously from the first-stage tank, gradually reducing internal pressure until the tank lost its structural integrity. When the tank collapsed, the sudden release of fuel vapor, combined with oxidizer gas inside the silo, produced an explosive mixture that ignited almost instantly. At the same time, nuclear weapons specialists focused on the recovery and examination of the WBU-53 thermonuclear warhead that had been thrown from the silo during the explosion. The warhead had landed approximately 600 feet from the destroyed launch complex, lying in a roadside ditch surrounded by debris from the missile. Although the blast had damaged some external components of the weapon, its internal safety systems remained intact. The W-53 warhead incorporated multiple independent mechanisms designed to prevent nuclear detonation unless a very specific sequence of commands and environmental conditions occurred during an authorized missile launch. These systems included electrical interlocks, environmental sensors, and mechanical safeties that prevented the firing sequence from beginning unless the missile was launched under controlled conditions. When the missile exploded inside the silo, none of the required arming signals were generated. As a result, the warhead's nuclear components remained dormant even as the missile that carried it was destroyed around it. Investigators later concluded that the safety features built into the warhead had functioned exactly as designed, preventing a nuclear detonation even under the violent conditions created by the explosion. Despite the successful performance of the warhead safety systems, the Damascus accident raised troubling questions about the broader safety of the Titan II missile program. Maintenance records reviewed during the investigation revealed that the system had experienced numerous technical issues throughout its operational life. The volatile propellants used by the Titan II, Aerozine 50 fuel, and nitrogen tetroxide oxidizer, were known to present significant hazards during maintenance operations. These chemicals were highly toxic, corrosive, and capable of igniting spontaneously when mixed. Technicians working on Titan II missiles had long been aware of the dangers associated with the fuel system, and maintenance crews were trained to follow strict procedures when handling equipment around the missile structure. However, the investigation revealed that accidents involving dropped tools and equipment had occurred previously during maintenance operations at other Titan II sites. Although those earlier incidents had not punctured fuel tanks, They demonstrated that the design of the silo environment made it possible for heavy objects to fall onto the missile if tools slipped from technicians' hands. The investigation also examined the decision-making process that unfolded during the 9 hours between the puncture of the fuel tank and the final explosion. Command personnel overseeing the crisis had faced difficult choices as they attempted to balance the risks associated with entering the silo against the dangers posed by the leaking missile. Some investigators later questioned whether the surrounding area should have been evacuated earlier, given the potential consequences of a large explosion within the silo. Although the Air Force had believed that the nuclear warhead would not detonate under such circumstances, the possibility of a massive conventional blast still posed risks to nearby communities. The rural location of the missile complex meant that the population density around the site was relatively low, but homes and farms existed within a few miles of the launch facility. In the end, the explosion occurred before any large-scale evacuation was carried out, leaving residents to experience the blast without prior warning. As the investigation progressed, the Damascus accident became a catalyst for renewed scrutiny of the Titan II program within the Department of Defense. The missile system had been introduced in the early 1960s as part of the United States' rapidly expanding nuclear deterrent during the Cold War. At the time, its powerful warhead and long-range capability made it one of the most formidable weapons in the American arsenal. However, by the late 1970s and early 1980s, the system was increasingly viewed as outdated compared with newer solid-fuel missile designs, such as the Minuteman series. Solid-fuel missiles required far less maintenance and eliminated the dangers associated with volatile liquid propellants. The Damascus explosion highlighted the operational risks that continued to accompany the Titan II system as it aged. In the years following the accident, the Air Force began accelerating plans to retire the Titan II missiles entirely. The decision reflected both the technological evolution of the nuclear arsenal and the growing recognition that maintaining aging liquid-fueled missiles carried significant safety challenges. Gradually, Titan II silos across the United States were deactivated and the missiles were removed from service. By the late 1980s, the system had been fully retired, replaced by newer missile systems designed with improved safety features and more stable propellant technology. Today, the site of Launch Complex 374-7 near Damascus, Arkansas, appears quiet and largely indistinguishable from the surrounding farmland that stretches across the region. The silo itself was destroyed by the explosion in 1980, and the remains of the complex were eventually filled and sealed. Few visible traces remain of the underground facility that once housed one of the most powerful nuclear weapons ever deployed. Yet the events of that September night remain one of the most dramatic nuclear accidents of the Cold War. A single drop socket had punctured a missile fuel tank, setting in motion a 9-hour crisis that ended with the destruction of a Titan II missile, the death of a technician, and the violent ejection of a 9-megaton nuclear warhead from its silo. The warhead safety systems prevented a nuclear explosion, but the accident exposed the vulnerabilities inherent in maintaining liquid-fueled intercontinental ballistic missiles on constant alert. The Damascus incident stands today as a stark illustration of the technical and operational risks that accompanied the management of nuclear weapons during the Cold War. It demonstrated how a minor mechanical mistake, a tool slipping from a technician's hand, could escalate into a disaster involving one of the most powerful weapons ever built. The explosion did not produce the nuclear catastrophe that might have been possible under different circumstances, but it revealed the fragility of the systems responsible for maintaining the nuclear deterrent. In the end, the accident contributed to the recognition that the Titan II missile program had reached the limits of what could safely be maintained, helping accelerate the transition to newer missile technologies that would define the next phase of the United States strategic arsenal.